Now, our next speaker has been in robotics for several years, I think it's fair to say. He has a degree in mechanical engineering, and he started his career in robotics and automation at KUKA. Later, he worked in marketing, adding robust understandings of business aspects and automation to his technical skill set. So please put your hands together for the head of robotics at Schneider Electric, Jens Bunsendahl. Welcome, Jens. It's a pleasure to have you here with us. This is for you.
Thank you very much. Thank you very much as well for the kind introduction. And I'm really happy to have such a big audience here on this Thursday, which is for me, as I'm the first time in Erlangen, a really, really good starting point for this presentation. As said before, let's go forward. My name is Jens Bunsendahl. I'm working as head of robotics for Schneider Electric Automation GmbH. So we are located with our headquarters in Marktheidenfeld, which is somewhere in between Würzburg and Frankfurt. What I'm showing you in the next couple of minutes is where we see some trends or some parts of the future of robotics. I'm not diving into some topics which were shown before by MechMinds, which were shown by Fanuc, where we have seen a lot of AI integration to enable things like grabbing into the bin, to enable special process parts. I could do this, but today my focus will be more on robotics integration into applications. So, having said this, Schneider Electric is doing robotics for more than 30 years. So we started with mechanics with Cartesian systems and later integrated the capability to control robot manipulators into our motion controllers. And from that point in time, we evolved from integrating robots into machine, then providing our own delta robotics, extending to full pick-and-place line control, adding more mechanics, introducing a new transportation system, which allows to move the products individually, to having our own our own twin solution, simulation solution. Cobot launched last year a new solution which allows to implement robotic applications much easier, more by configuration than by programming. And right now we are finalizing our new offer, the SCARA, which shall be launched this year. So, what we have seen, for example, from MechMinds, from Fanuc, I would put it more into the area of technical feasibility. With AI, with additional sensors, you can enable applications. And this is the basic for automation. But this is what I'm not focusing on in my presentation. When I speak to customers, when I speak to integrators, in the end, it's all times coming back to cost. If people are going automation, and especially in industrial automation, they are doing an invest and they want to see a return. So you start to discuss and you end at costs. One of the things where we can influence cost is performance. If the robot is faster, you could produce more, or if you're running multiple robots, you might use less robots. So either more throughput or less cost when you invest in your system. Engineering can influence a lot of things. You could reduce your engineering costs. You could do an engineering which achieves a faster time to market, which means you can offer faster than your competitor. You are able to sell because you are quicker, because you are more efficient in engineering, or you have simply the better engineering quality. And another topic is, once a system is applied, it's in operation, so you have to operate and you have to maintain it. There are several other aspects influencing the costs, but today I would like to focus on these three. Starting with the performance, and here I'm start with the chocolate ball. I think you have seen a lot of these. You might have eaten a lot of these. And some years ago, we had a customer doing a very, very simple task. So the chocolate balls were coming out of the production machine, large area of chocolate balls, and the task was then to put it into a wrapping machine which was then simply doing the wrapping. Sounds fairly easy. Taking the product, putting it into the wrapping machine. The nice thing is that these hollow chocolate balls are made from two halves. You can pick it easily with a suction cup, you can move it, you can place it. Very, very easy. But if you now start to increase the performance and you increase the robot speed, you increase the acceleration, you end up with a very nice problem. Because you end up with separating the chocolate balls. So if you see this little seam where the two parts are put together and they are lying exactly horizontal in the form, and you take it out and then you accelerate with 2G, 12G, 13Gs, you separate. So the product cannot cope with the robots anymore. Which means for some applications it doesn't make sense to increase the robot speed, to increase the acceleration, because we have reached the limits what the products can cope. We have reached the limits what the grippers can hold. We have reached sometimes the limits of mechanics. Trying to optimize here will not help. So if we want to then improve performance, what can we do? And the answer is we have to enlarge the scope. Instead of just making the robot faster, we have to make the whole application faster. And what you see here is a machine which was built for Schneider Electric, which is manufacturing circuit breakers. This was done by two machines before. Now it is done in one machine. The machine is 60% faster than the two machines before. It can do 80% more variants. How did we achieve that? One of the big things was to eliminate wait times. If I'm controlling the whole application, then I know all the movement in the machine. I know exactly these kinds of movers. So I can start the robot way before the mover is in its target position, because I know when it will be there. So instead of using some semaphores to say something is in place, we are running all the motions completely synchronized. So no wait times. Second thing is flexible transport system. There's always some jitter from the systems feeding in components as they are running a little bit different cycle times and the cycles done by these processes. By transporting the products individually, we can vary the speed. So we can catch up if necessary, we can compensate the jitter. So we can always run the system at full speed. And if you have run the system fully synchronized, also the nice tricky situation, if somebody is pressing E-stop, the whole system has to stop. It stays synchronized. You can immediately restart, which is also a gain of products manufactured in an hour. So one thing is not consider just the robot, consider the whole application and treat it as one, not putting a robot in the center and then put some components around. Treat it as one application which is controlled, completely synchronized. Second thing is, now going to the engineering, go more to predefined mechatronical units. Why? So on this slide you see the same application two times. On the left-hand side, it is a design which was done in 2005. And the idea behind was to build a very flexible machine. So you see here some infeeding system, put it into a racetrack. The racetrack is doing the grouping. Here we have the robots putting a carton box on the belt, taking the group products, putting it on the carton box, closing the carton box, moving it out. The idea here was using robotics for the flexibility, because robots can be driven by software. So here we see already the idea of software-driven motion. At that time, the customer had to design the robots. We were able to drive the system. They had to design the racetracks. We offered the software to drive it, and then he could operate it. So a lot of engineering effort around. In 2023, another customer did a very, very similar machine. This time, he used standard components. He bought the robots from us. He used one robot he designed on his own, and he integrated the multi-carrier, flexible transport solution. What is the big difference? Much less mechanical engineering, because he used more standard components. With the multi-carrier system, there is a transport system available which is completely scalable. It's built from bricks. If you need it bigger, you just take more. So instead of designing a racetrack for a specific kind of components, you can just take the system and scale it. A very flexible mechanical component, which is as well software-driven. All these movers are software-driven. So now we do not just have software-driven motion. We have software-driven motion, flexible software-defined motion implemented on standard components. So the design time, mechanically, electrically, is going down because you have a set of standard components which you are recombining. And the functionality provided is then implemented, defined by the software. Much different way of doing it. So what we got as figures from the customer is that by doing this, he ended up with 40% savings on this machine. Even though this transport system by itself is a more expensive solution than a simple racetrack. But by redesigning the machine, he got rid of many, many components, as this system is taking over a lot of functionalities which was done by different systems before. He could done the engineering much faster, as it's simply done from the same components, and he got in on top more flexibility. And the important thing is, this is not just a mechatronical approach. Because if a machine is built more from standard components can be supported in a better way. With a robot, we can provide the corresponding model in the twin. With the transport system, we can provide the corresponding models in the twin. Now we are able to simply put the machine concept together in the twin by just putting together the concept. As we know it, we are able to simulate it immediately. And if we have a model which is working, we can immediately start to do an optimization. For example, using AI to optimize the number of carriers which are required to run the application with best performance. If we know the components, then we can generate a large part of the software, because then we are coming from programming all the stuff to describing the application, describing what shall the robot do. For example, telling the system, this is going to be a pick-and-place process. And we are starting to try it out with 4 robots, 2 conveyors. We are describing the product patterns which are coming into the machine. Then we can simulate immediately, and you can see, okay, the system is capable to handle, or perhaps I need a robot more, or I can remove a more robot. But this is no longer that I have to write all the code. By having everything together, by being able to describe it, we can simplify the product so far that we can generate parts of the applications. And if I can do this, and I have the model available, then I can also immediately start with virtual commissioning. And this not on robot level, this is then done on application level. So, and this, in the end, results in a much shorter time to market. This is how the customer before shortened the engineering cost, reduced the engineering costs and shortened the time to market. Putting together standard components, running, simulate immediately, optimize it virtually, and then build it. And of course, using predefined components which are used for longer times on the market also results in a better quality. But here, the robot by itself, it does not exist anymore. Yes, it's a mechanical piece, but it's no longer the picture of having a robot in the center of everything and something around. Now the robot is just a piece of mechanics which is controlled like all the other parts of the application. And why is Schneider investing a lot into also robotic mechanics? Because we want to provide the robot or the mechanics really suitable to the process. Some things can be done with Delta robots in a very good way, others can be done with Scaras or cobots, but we want to be the one who can provide the right mechanics and, of course, support it in our engineering environment in the same way. Coming to the engineering environment, which is also very important in operation, from our point of view, it is a big benefit to have a single software ecosystem, because I want to do the application independent from the mechanic used. In the moment I have to change my engineering environment, if I use a different mechanics, I have to train again all my engineers. In the moment I'm using different kinds of controllers, for example, different robot controllers, then I have also different kinds of commissioning and especially different kinds of diagnostics. So if I'm able to harmonize it into one software ecosystem, if I'm able to harmonize it into one architecture, I will simplify, I will reduce training costs, I will simplify the maintenance of the fleet in the field. However, we as Schneider will never be able to supply all the components which are the best for a certain process. So the system must be open to integrate third-party components, must be open to integrate self-developed components. Also a very, very important property in the future, to have an open system which allows to integrate almost everything. Another side effect, if I have everything in one, also cybersecurity would be easier, so I have to then maintain one platform and not several. So, summarizing, where we see the big benefits and where we see also the future. If we want to increase the performance to reduce the cost of ownership, we have to take care on the application. We will have to take care much more on synchronizing all the components together, not with semaphore, but really real-time synchronization on a millisecond level. We can improve on the engineering by providing mechatronical modules, which are in the end software-driven mechanics, software-driven motions. And if I talk about a component, it's not just a mechanical component, it's a mechanical electrical component with the virtual counterpart, so that I can really start with simulating it out of the box. To harmonize, to simplify operation, from our point, it's good to have one engineering environment which can integrate all the stuff, which can run all the thing as one system and not distribute on several different control systems. So, having said this, I'm done with the presentation, so still some minutes left. Feel free to ask questions, comments, whatever.
Thank you very much, Jens. Who has a question? Which company are you with now for this question? Or not with?
Oh, no, everyone knows. So I do like the idea of having everything synchronized, right? That's, I think, for a PLC programmer, the best you can imagine. I did see a cobot. Is that one also fully synchronized in your system?
So we have fully synchronized, let's say, all the deltas. We have fully synchronized the Scaras. We have not fully synchronized the cobot so far.
Yeah. Is this something where, again, SLCI could play a role? So would you see that as an option to make it easier to?
So one of the big drawbacks from our point of view of SSCI is that it's not doing fully synchronized motion. So as we see the benefit in fully synchronized, we are in the moment putting the focus on providing the platform for synchronized motion.
Yeah.
Of course, there are lots of applications where commanded operation is good enough. So I will not say no, or so I will not say that we will never support it. In the moment, in our strategy, we see other opportunities which are better for our business in short term.
Yeah. But when you look at the cobot, typically the speeds are a bit lower, especially when it's working in collaborative mode. So the whole synchronized thing is, I would say, probably less of a topic there.
Yes, if you look to the articulated in general, they are normally running at much lower speeds.
Yeah.
Yes, there are some applications which benefit from synchronization, but many of these 6-axis articulated are often quite simple loading, unloading operations, where you have not this focus on the tight synchronization.
Yeah. But when it comes to 6-axis robots, so are you saying that you are focusing on like implementing it completely yourself, so to reach that goal?
Yes.
And the focus is on that. Huh. And if a customer, let's say a Schneider customer from France, asks, can we also use a different robot from a different vendor, let's say Fanuc, could then such a library be
the system is
possible?
open.
Yeah.
So the transformations are there. You can configure it. If you speak about vendors like Fanuc, you have to interface. So then the big problem is how to interface these systems. Either, from our point of best, we are interfacing the motors immediately, which I think is a little bit difficult with Fanuc as they have their own encoder systems, or you put the controller in between. But then you're ending up with a situation that you have the controller, which you have to diagnose and so on. It's different. This is one of the reasons why, for the moment, we are providing a lot of robots on our own.
Yeah.
Because this market, especially for 6-axis, it does not really exist. So it exists for other kind of mechanics, like for the Delta robots. So in Germany, there is a company, Autonox, which is quite strong here. They are also started to build up 6-axis. But what I think is, if I speak from the perspective of PLC builder, it was easy to start in the Delta robotics. It was a niche at that time. So we are growing out of it, supporting much more mechanics. And we are not the only ones, so we can see it, or you can see it also at other PLC vendors. So the market of open controllers capable to run a large variety of different robots, like SCARAs, like 6-axis, is growing. And I think these will also foster other companies providing these kinds of mechanics as open mechanics, which are then easy to integrate.
Thank you.
Okay. Thank you very much. We're going to have to wrap it up there on the time, but I'm sure Jens is happy to answer any more questions during the break. So, round of applause. Thank you very much, Jens Bunsendahl from Schneider.